So when you guys studied Z transform in 345, you dealt with the poles and zeros and tried to figure out where the poles lie, where the zeros lie. You looked at it from the perspective of stability and all those other questions. But what we are really interested now is what do the poles and zeros mean in the context of frequency response? What do the poles and zeros mean in terms of digital filters itself? If I just show you the pole zero diagram of two filters, what you can say about the two filters. So this discussion is primarily about FIR filters. So I want to remind you that if a filter has Z transform, let's say H of Z, then the zeros of the filter correspond to values of Z for which H of Z is identically equal to 0. So as the name implies, the zero of a filter is where the H of Z, the Z transform of the filter takes the value 0. And if you look in the Z plane, this is your unit circle, you will often see diagrams like you will have a 0. For example, you might have two zeros around this region, and that just says that your filter has zeros at these two locations. Okay. Now, we won't be talking in this lecture much about the poles, but of course the poles are similarly defined as values of Z for which H of Z equals to either plus or minus infinity. So poles in the Z transform domain are often shown using crosses. Okay. So you'll often get pictures like this, which means it has two poles and two zeros. Now, even though you may not have realized it, but poles and zeros really tell us a lot about the filters and their properties. So for example, the first thing is that an FIR filter has no pole except possibly at Z equal to 0 at the origin or Z equal to infinity. Okay. An FIR filter has no other pole in the body except at the origin and at infinity. So how do we show that? Well, let's take the example of an FIR filter, which is given by simply the convolution formula, m from minus infinity to infinity, h of m, x of n minus m. This is just the convolution equation for if you have a filter hn. You input xn, you get yn, and yn is given by convolution formula. Now, this is an FIR filter, which means that the filter is 0 for all values except a finite range. So let's assume that the filter is zero only, is non-zero only for from minus n1 to n2. Okay, and 0 is somewhere in between. So it's non-zero only for these values. So in that case, I can simply replace the summation from n from minus n1 to n2 hm x of n minus m. Okay. So right now we have used no other property except that it's an FIR filter. Right? So what is now the Z transform of an FIR filter? We know the trick. We'll just take the Z transform of the left and the right hand side. So I get Y of Z equals summation M from minus N1 to N2. H of M Z to the minus M X of Z. And then I take the X of Z to the other side, so I get Y of Z over X of Z. That is simply H of Z, the Z transform of the impulse response. And that is given by summation M from minus N1 to N2 HM Z to the minus M. So HM is, of course, just some numbers, right? So let's call these numbers as, let's say, AM. So I'll denote these numbers by AM. So H of Z is summation M from minus N1 to N2 AM Z to the minus M. Right? So the Z transform of every FIR filter is simply a polynomial in Z to the minus 1, and the coefficients of the polynomial, right? The coefficients of the polynomial so the coefficients correspond to the values of the filter. For example, if I give you, so an example is someone says H of Z equals, let's say, 2 minus 3Z to the minus 4. Okay. Now, just by the fact that it's a polynomial in Z inverse and it doesn't have any denominator polynomial, you can make some conclusions. Number one is that this is an FIR filter. Okay. Just by looking at it. And number two, you can write down the values of the FIR filter. You can write down H without doing any inverse Z transform. You can just write down, by writing down, you know that whatever corresponds to Z to the minus M is the filter value at mth location. So what is H of, so what is at n equal to 0? That's the coefficient associated with Z to the 0. So that's 2. What is n equal to 1? Well, I don't have Z to the minus 1. So that means it's 1. What is n equal to 2? Again, I don't have the Z to the minus 2 term. So that's 0. What is n equal to 3? Again, I don't have the Z to the minus 3 term. That's 0. And what is n equal to 4? That is the coefficient associated with Z to the minus 4. That's minus 3. Okay. So there is a one-to-one correspondence between the Z transform, the polynomial that you get for an FIR filter, and its coefficients and the values of the filter. Now you can just draw the filter. This is 2 at n equal to 0, 0, 0, 0, and then at minus 3 at n equal to 4. Right? This is your Hn. So one thing is very clear, that if you are given a Z transform, you can just look at the Z transform and decide whether it's an FIR filter or an IIR filter. Okay? If it's not FIR, then the only other option is it's an IIR filter. Right? So that is one thing. Now the other thing we started with is that an FIR filter has no poles except at z equal to 0 or z equal to infinity. So how do we verify that? Well, we again look at this red blocked equation. So the one thing we note is that this is a sum of finite terms, right? So z transform of an FIR filter is simply a sum of finite terms. How many terms the Z transform has? It has no more than the length of your FIR filter. If your length of the FIR filter is 10, you don't have more than 10 terms. Right? So if we look at that, then it's clear that we cannot add a finite number of values to get infinity. So what's the definition of the pole of a Z transform? That h of z equals infinity, right? So there is no way that we can add up a finite number of finite values to get infinity. Okay, so as long as each term of h of z is finite, this means that h of z will be finite. A absolute value of h of z, right, is going to be less than infinity. Okay. So what are the cases that any of the terms can be infinite? What are those cases? Well, there are only two cases. The first case is that if n1, so let me actually replace this. Let me replace this from minus n1. Let me write it as simply n1. So two numbers. It goes from one number n1 to n2. So the first case is that n1 is less than 0. So if n1 is less than 0, you have in your Z transform terms with positive exponents. So then you have, for example, a term like z to the 10. If n1 was, let's say, if n1 was minus 15, then you have, for example, term like z to the 10. So this means that if you input z equal to infinity, then h of z will be equal to infinity because one of the terms is infinite. So that is the only case when you can get a pole. And then the next case is that if n2 is bigger than 0, then you have terms with negative exponent. For example, if n2 is 15, then you can have a term like z to the minus 10. Well, z to the minus 10 is simply 1 over z to the 10. This means that if I input z equal to 0, then absolute value of h of z will be equal to infinity again. So these are the only two cases for an FIR filter that your Z transform can have a pole. Okay? An FIR filter has no pole except at Z equal to 0 or Z equal to infinity. And it has a pole at Z equal to infinity. So what is this condition? N1 less than 0 means that your filter Hn has a non-zero value for n less than 0. Okay? So you can translate that, right? An FIR filter has a pole at z equal to infinity if and only if h of n equal to is not equal to 0 for some n less than 0. Right? That's the only condition that you can have a pole at z equal to infinity. Now, a filter which satisfies this condition, that the filter has a non-zero filter coefficient for n less than 0, that is called, so that's called a non-causal filter. Okay. So if you are given a pole zero diagram of an FI of some filter, and the filter has no pole except at z equal to infinity, and maybe z equal to 0, but if it has a pole at z equal to infinity and no other pole, then you can conclude that that filter is an FIR filter, and at the same time it's a non-causal filter. So this is a non-causal FIR filter. Okay. So you can, the corollary of this is that a causal FIR filter only has poles at z equal to 0 and has no other poles. Okay. So we have talked about nothing except the poles and zeros, and we have reached the conclusion that if someone shows you a pole zero diagram and the diagram has no poles except at z equal to 0, then you will make two conclusions. Number one, it is an FIR filter, and number two, it's a causal FIR filter. So now we can just write down the general expression for an FIR filter Z transform. So the Z transform of a causal FIR filter is an mth degree polynomial in z to the minus 1. So you will have h of z equals to a0 plus a1 z to the minus 1. It will keep on going, plus am z to the minus m. So it's an mth degree polynomial, and a0 corresponds to h0, the next coefficient corresponds to h1, and hm corresponds to h capital M. So if you have an mth degree Z transform, then the other conclusion you can make is that the length of the FIR filter is capital N, the length is equal to M plus 1. So just like in the previous case, we had a fourth degree polynomial, and of course the length of my filter was 5, from 0 to 4. Right? So that is another conclusion that we can draw. And the next thing is that if you remember the order, right, if you plug in z equal to 0 in this expression, then you are going to get infinity. And so because of the degree of the polynomial, this filter has a pole of order m at z equal to 0, right? Or a pole of order length minus 1. So order m is effectively order length of hn minus 1 at z equal to 0. So that was the discussion about the poles of FIR filter, which is very simple discussion. But what about the zeros? We haven't so far talked about the zeros now. So the question is, what do the zeros of FIR filter tell us? The poles don't give us much information except the order and whether it's causal or non-causal. So what do the zeros tell us? Well, they tell us many things. Some of the things we'll study later in terms of whether they are conjugate pairs or not and how they are located. But one of the key things that they tell us is they help us interpret the frequency response of a filter. And the zeros of whether you're talking about actually an FIR filter or an IIR filter, the effect of zeros is exactly the same. But since right now we started talking about FIR, I'll focus on that part. But remember that even when a zero appears in an IIR filter, it will have exactly the same effect. So to explain the effect of zeros, let's focus on, so let us consider the case of a length 2 filter. Okay. The simplest filter that you can consider, it's a length 2 filter. So if it is a length 2 filter, then my h of z is simply given by a0 plus a1 z to the minus 1. Right. Now, I will write that in a general form. I'll write that as, I'll take a0 constant, I'll get 1 plus a1 over a0 z to the minus 1. So where is the 0 of this polynomial? First of all, of course, we know from the fundamental theorem that if you have a polynomial of degree m, then how many roots does that polynomial have? M. So this polynomial has only one root, so it has 1, 0, and that 0 is given by z equals minus a1 over a0. So that's the location of your 0. So in general, if I have a length 2 filter, I'll now write it in a more simpler form. I'll say that my filter, if I know the roots of the polynomial, we can write them in factor form. I'll just write it now as h of z is equal to p0 some number times z minus zeta 1. Okay. So this means that I have a 0 at z equal to zeta 1, right? Now, what's the relationship of the z transform to the frequency response? That relationship comes from understanding that the Z transform and the DTFT are related to each other through the DTFT is just the Z transform at the unit circle. So we know that the frequency response h of e to the j omega, and in particular, let's focus on just the magnitude response right now. So that is equal to absolute value of h of z for z equal to e to the j omega. Okay. So the frequency response is simply the magnitude response is absolute value of p0 times e to the j omega minus zeta 1 absolute value. So now let's consider the effects of, so this is my 0. Let's consider the effect of the 0 on the frequency response. So let's treat this as, we'll just use simple vector knowledge that we have gained over the years, high school and in college. So treat this as a vector, e to the j omega. So you are interested in evaluating, now this little omega is a particular value of the frequency. Okay? So you are in the z plane and you are interested in, let's say, evaluating the value of your frequency at this location. So this is a point e to the j omega, or you can think of it as a vector e to the j omega. Right? So if I treat it as a vector e to the j omega, then all you are asking is what is the length of this vector. Right? So e to the j omega is just the length of this e to the j omega absolute value is just the length of this vector, right? Okay. So this is one vector R1. Call this the other vector R2. So what is the other vector R2? That is where your 0 is. Right? So let's say that your 0 is here. So this is the location of your 0. So this is your vector R2. So what is the expression for absolute value or the magnitude response at frequency little omega telling you? It is telling you that you are looking at the vector R1 minus R2 and you are looking at the length of that subtracted vector, right? So that is just the, you are subtracting just two vectors, right? The length of that vector is this one. So what this says is that as you change the contribution of your frequency, the contribution of your filter at frequency little omega, that is directly given by the difference between the vector that is sitting at your pole and the vector that goes from your origin to the frequency you are interested in. You are really looking at the length of this difference vector, which is this. Right? So if you imagine this, that as I take, so I'll draw it a little bit bigger. So this is my 0. I have only one 0, and that vector is fixed. Okay, but the other vector is changing as I go from little omega equal to 0 to little omega equal to pi and all the way back, right? So you are starting, the other vector is starting at, so for little omega equal to 0, you are starting here, and the length is this much, right? This means that if the 0 is very far away from omega equal to 0, your magnitude response is pretty high. I mean, P0, I'm ignoring the effect of P0 because that's just a constant, right? That will scale everything the same way. But let's just consider what is happening. When I am at omega equal to 0, my length of the vector is pretty high. Right? Now I slowly move. I am interested in, let's say I get interested in frequency omega equal to pi by 2. So my vector is this, and the difference vector is this part. Right? Now my difference vector has shrunk. And why it has shrunk? The length of the distance vector has shrunk because I'm getting closer to the 0. I'm getting closer to the 0. And when my frequency that I am interested in is perfectly aligned with my 0, the difference vector is going to be the smallest. The difference vector in the same direction as my 0 is going to be the smallest. That means that around at the direction of my 0, I will have a dip in my magnitude response. Okay. So to make it more concrete, let's take the example that zeta 1 is equal to, I'm going to write it in polar form so that it becomes very clear which direction my 0 is. Let's say it's 0.5 e to the j pi by 4. So now I am actually drawing my 0 in the first quadrant. Okay. So my 0 is in the first quadrant, the distance from origin is 0.5 and the direction is pi by 4. So without knowing anything else, without even knowing the value of P0, just using the thing that I told you, right? This is your 0 frequency, omega equal to 0. This is omega equal to minus pi. This is omega equal to pi. The closer you are, and this is pi by 4. The closer you are to the direction of the 0, right, the smaller your magnitude response will be. So without thinking, like you cannot draw it exactly, but you have a sense that your magnitude response will look something like this. Now, how far it will go down, how far the magnitude response will go down. So where it will go down is a function of the direction of your 0. But how far is it going to go down? What is that a function of? So the amount of dip that a 0 creates is given by how far away you are from the unit circle, or in other words, if I call this the radius, the magnitude r, then it's really about 1 minus r absolute value. Okay, so that's the amount of dip. So if my 0.5 became 0.75, then this will dip even further. And if my 0 was exactly on the unit circle, if my 0 was exactly on the unit circle, then my frequency response at that point will be exactly 0 at that frequency. So by placing the 0 appropriately, you can figure out what you want to do with your frequencies. For example, if you are interested in eliminating just one frequency in your system, which is pi by 4, what you should do, put a 0 at e to the j pi by 4. Right? and you will have a filter which kills the pi by 4 frequency. So let's summarize that last point that I said, that if we have a 0 at e to the j, let's call it omega naught. So if we have a 0 that is exactly on the unit circle with direction omega naught, then this means that h of e to the j omega naught, at that value, our frequency response will be identically equal to 0. Okay. Otherwise, it will be a function of how close you are to the unit circle. And the second thing is, the closer zero is to a unit circle, the more attenuated your frequencies are at or near the direction of the zero. Okay. So direction of the zero tells you the frequencies which will be attenuated, and distance from the unit circle tells you how much they will be attenuated. Okay. Now, we started with the case of just 1, 0. But what about the case of what about length n equal to m plus 1 filter? Well, in that case, your z transform is an mth degree polynomial, and an mth degree polynomial has m roots. Some of them may be repeated, that's different case, but it will have m roots. So we can write that h of z as p of 0. So this is the multiplication. You are multiplying k terms, z minus eta k. This means your zeros are, you have m zeros. They go from 1 to capital M. Okay. So what is the effect of that? Well, again, we can just write down what we wrote earlier. Absolute value of h of e to the j omega is simply the z transform evaluated at the unit circle, and then absolute value of the terms being multiplied is just, we can take the absolute values inside, so I get p0 absolute value, which is just a factor that affects all frequencies equally. It's not a function of little omega. K equal to 1 to m e to the j omega minus zeta k. So now what we see is that effectively each one of the zeros contributes to the factor that we saw earlier. And then collectively all of those contributions get multiplied. So each zero contributes a multiplicative factor to the magnitude response. And the total magnitude is simply product of all those factors. So if I take the example of, let's take the example of 2 zeros to make it clear. Okay. So let's say I have a 0 let's work with this pi by 4 direction. I have a 0 in pi by 4 direction. So this is going to pull down the frequencies in the pi by 4 direction. Right? With frequencies that are near pi by 4 are going to be pulled down because it's 0, it's pulling it down. Now let's assume I have another 0 in the same direction on the opposite side. Okay. What is that 0 doing? Well, that 0 is contributing another factor, and if it is very close to 0, then the factor is really small. So effectively, by placing two zeros in the same direction, I get to pull the magnitude even further. Right? So let's assume that I had zeta 1 equal to 0.5 e to the j pi by 4. And I had zeta 2 equal to 1.5 e to the j pi by 4. So one inside the unit circle, one outside the unit circle. Well, one of them, zeta 1, is going to contribute absolute value 0.5 in the direction of pi by 4. The other is going to contribute another 0.5. So my total, assuming P0 is just 1, my total magnitude is going to be 0.25 or 0.5 squared. So if with one 0 in pi by 4 direction, if I was coming down up to this point, 0.5, now with two zeros in the same direction, I am now going to come down even lower, up to 0.25. And similarly, if you have many zeros, then the cumulative effect of them is what you're looking at. So let's do a concrete example to get a better sense of this. So the example is a moving average filter, which we have seen before. So assume that h of n is 1 over m for n from 0 up to m minus 1. So it's a moving average filter. It just averages m contiguous values. Now, if you want to compute the z transform, it's trivial. You just write a polynomial where the coefficients of the polynomial are simply the values. So it's 1 over m, n from 0 to m minus 1, z to the minus n. Okay. Now we can use the geometric sum formula, and we get 1 minus z to the minus m over m times 1 minus z to the minus 1. So a couple of things that we should be careful about. So a moving average filter is an FIR filter. And we talked about an FIR filter being given by a simple polynomial with no denominator polynomial. But why is the z transform of a moving average filter actually consisting of a numerator and a denominator polynomial? Is then it not an FIR filter? Well, superficially it looks like it's not an FIR filter, but actually the numerator polynomial has a factor, right? It can be written as 1 minus z inverse and another polynomial divided by m or 1 minus z inverse, and so the factors get cancelled, right? And the other way to see it is that the numerator polynomial has m roots and the denominator polynomial has one root, and the numerator and the denominator polynomial share a root. So that's the common factor that gets cancelled. Okay? So looking at now the zeros, so the zeros are the roots of 1 minus z to the minus 1, or effectively the values of z for which z to the minus m equal to 1. So this is just the mth root of unity that you are trying to solve, and so the roots that you get are e to the k, e to the j 2 pi over m times k, where k goes from 0, 1 up to m minus 1. Okay, you have all of your roots are living on the unit circle separated by 2 pi over m, right? Just like you do it for the cube root. And if you look at poles, which are the pole is really simple. The pole is simply at z. So you have a pole at z equal to 1. Okay, so let's call that lambda 0. That is at 1. So as you can see, the numerator polynomial has a root at 1, and the denominator polynomial has a root at 1, so you have a cancellation of that. So this, in reality, this moving average filter of order m has m minus 1 zeros, okay, and those zeros are separated by 2 pi over m except at around 0. So what you have is those zeros are, you have no 0. So first of all the zeros are on the unit circle. All the zeros of a moving average filter are on the unit circle. Okay, and they are separated by 2 pi over m. So this is 2 pi over m, and you keep on going, right? But you don't have any zero around omega equal to 0 because of the pole 0 cancellation. Okay. So the concrete example of, let's say, if you have m equal to 4, if you have m equal to 4, then you have zeros at the 1 equal to e to the j 2 pi by 4, e to the j 4 pi by 4, and e to the j 6 pi by 4. Okay. These are the three zeros that you get for m equal to 4. So those zeros will be, and they are on the unit circle. The first zero is at pi. Okay. At pi by 2. The second zero is at pi, and the third zero is at 3 pi by 2, right? Or minus pi by 2, whichever way you want to look at it. Okay. So this is the moving average filter. And now, just by the discussion that we had, so you have three zeros. A, you figure out which directions these zeros are. So if I'm trying to now find out the magnitude response, so I'm trying to now find out the magnitude response of the moving average filter. And let's focus only from minus pi to pi. This is 0. First of all, I know the directions of these zeros. So the 1 0 is at pi by 2. 1 0 is at pi or minus pi. It's both the same. And the second 0 is at minus pi by 2. So one thing is, I know that in the direction of the zeros, my magnitude response will be pulled down. Secondly, how far the magnitude response is going to be pulled down is going to be a function of how far away the 0 is from the unit circle. Now in this case, the 0 is exactly on the unit circle, which means my magnitude response will be pulled down exactly to 0 in those directions. So if I had to even guess what will it look like, I will have my magnitude response will hit 0 at minus pi by 2, and it will hit again 0 at pi by 2. Okay. And then it's going to go up, but then it's going to hit again at pi, it's going to hit 0. Okay. Now, you see, and that comes from just intuition. You see that I have kept the height of the magnitude between pi by 2 and pi lower than the height around 0. And the reason for that is because the zeros here are close to each other, so they are still pulling even away from the direction, they are pulling the values down further. Right? So just by having no other knowledge than just the location of the zeros and the direction of the zeros, you are able to tell something about the response of your FIR filter. So the question that was asked was, why didn't I draw the 0 at 0? And the answer is because the numerator had a 0 at 0, but the denominator also had a root, which is the pole at 0, and the 0 and the pole got cancelled. Right? So you factored them out, and that's called the pole 0 cancellation. If you have a pole and a 0 at the same location, they cancel each other's effect. Now you can provide a similar understanding can be provided for the phase response. For magnitude response, you are looking at the length of those vectors. Now it should be very simple that for phase response, you would be looking at the phases of those vectors, of the difference vectors. Okay? So if I'm looking at the phase of my frequency, if I'm looking at the phase response, that is simply equal to the phase of the factor P0 that I wrote earlier. Okay, minus little omega capital M plus, you will sum up the phases of all of those difference vectors that we saw earlier, e to the j omega minus zeta k. Right? So these are the difference vectors from which frequency we are interested in to where the 0 is. And you add up all those phases and you get your phase response. But of course, for many zeros, drawing the phase response is not that simple. So we won't go into the details of that, but at least magnitude response is very trivial to evaluate. And one of the things that you can play with in MATLAB is called FV tool. You have seen that earlier too. Can be used to play with magnitude response, magnitude slash phase response, and the locations of the zeros. So here is an example. I just generated that moving average filter with m equals 4, and I just use an FV tool. And indeed, now FV tool, in this case, it's just showing you the 0 to pi frequencies. So indeed, you see that you have, this is in dB, so it's really going to minus infinity dB. You have a strong dip at pi by 2, and then again at pi. And you see that the height, the maximum height at 0 is much higher than the height at, which is between minus pi by 2 and pi. Okay. Now you can play with this. So you can look at the phase response by clicking on this button of the FV tool, but the more interesting thing I want to focus on is this pole zero plot. So in this pole zero plot, here are the zeros, and I can actually play with these zeros, and I can edit them, and depending upon where my zeros are, I will get a different response. So here is another example of a moving average filter now with m equal to 10, right? And again, the same effect will take place, that you will have now nine zeros, and the zeros will be separate. You will still have the cancellation, so you will have no zero at little omega equal to 0. But you will have zeros every 2 pi over 10. So that's pi by 5, right? And you see that indeed every pi by 5 you have a 0. So your magnitude response hits 0, goes up again, hits 0 again, goes up again, hits 0 again, goes up, hits 0, goes up. Okay. And if you look at the pole zero diagram, indeed you see that around 0 you have nothing. And then you have every pi by 5 you have a 0. So this, if you keep on increasing the order of this FIR filter, you will start bunching more and more and more zeros, and you will have more of those ripples. And the reason is exactly what we looked at, that a 0 is pulling down the frequency response, and if you have more zeros, then you have sort of more of these ripples and so forth. Okay? Now, placing these zeros, if you learn to place the zeros in the right fashion, which is the other tool that we'll look at it later, the FDA tool, that allows you to actually even come up with frequency responses that are not that are somewhat arbitrary, that satisfy your needs. Okay, so that's really, in digital filter design, figuring out where to place the zeros and poles helps you actually design filters that meet your specific needs.